Welcome back, folks. We're going to take a look at an example of maximum power transfer theorem, and it's going to be a larger circuit. We can take two different approaches to this. So we can go find the Thevenin equivalent. We can go find the Norton equivalent. Really shouldn't matter, but this is kind of a typical question that you might be asked to answer on an exam. It's certainly a little more academic, but the principles still apply if you were to use it in a more practical setting. Okay, so let's get that example. Looks like that. And what is the maximum power RL can dissipate? Okay, so we have RL over here, and we want to know how much power it can possibly dissipate. So if we're talking about maximum power, the first thing we should do is go find an equivalent circuit. It doesn't matter what it is, just go find an equivalent circuit. I'm going to do a Norton equivalent just because we've been looking at Thevenin a little bit and back and forth. I just want to give you another look at Norton. And then once we find that Norton equivalent, we'll just make the resistances match, and we'll go calculate the power from there. Okay. So in order to do that, find the Norton equivalent, we are going to remove the load if drawn. Okay, and we need to find I short circuit, so we replace it with a short circuit current there. Go do the analysis any way you want. We're going to do this with mesh here. Okay, I2, I3, and I'm going to do that because I'm stinking fast at it, and I'm pretty good at it, I think. My mother's real proud. That's what I got. Okay, so it's going to be a 3x3. Let's see, I need to get a little more on the screen here. So what does I1 touch? There's one, before I do that, there's one current supply. It's down here in I3, so there are no super loops. So we're going to write one KCL and two KVL. So let me do the KVL for I1, the KVL for I2, and then I'll finish it off with the KCL for I3. So for the KVL for I1, what does I1 touch? It touches 2, 3, 4, 5. Okay, so that's going to be a total of 14. What does I1 share with I2? It shares the 4. And then what does I1 share with I3? It shares the 5. All right. Remembering that we're going to invert all of this at some point. And on the right-hand side, we're going to go up 24. So we have positive 24 on the right. Okay. KVL for I2. What does I2 share with I1? It shares the 4. What does I2 touch? It looks like it touches a total of 5. What does I2 share with I3? Nothing. And then what, any voltage supplies? Nope. So that's going to be a 0. All right. Not too bad so far, right? Love that shortcut. Gotta love that shortcut. Okay, we're writing a KCL now, so the questions change a little bit. Does I1 touch the current supply? Nope. Does I2 touch the current supply? Nope. Okay, so those are both zeros. Does I3 touch the current supply? Yes, so it's a 1. And it goes in the opposite direction, so it's negative. And that's equal to 2. Okay, so we're going to solve this. Hopefully you're following along and practicing with whatever tool you use when doing your work. We're going to solve that, and it's going to give us our vector of unknowns. Still over my left shoulder, depending on how this is mirrored. But let me go ahead and do that. I have not worked this problem in advance. I do know what the answer is, but hopefully we get that answer, right? I haven't worked it out beforehand. I like working it out live. That way when I screw up, we all can learn from it. Because I will screw up. Okay. Let's see here. So we've got I1 is 1 point, I'm going to call that 30 amps. I2 is 1.04 amps, and I3 is, oh, it's negative 2 amps. It better be, right? Okay, now it's a little bit behind me, but not too bad. Those are our currents. So we have part of our Norton equivalent, right? I'll draw it up here. We have part of our Norton equivalent. We're going to hook up our load out here. And this is going to be R Norton. Here's I Norton, and now we know what that is because I short circuit. I can write it just above my head. I short circuit is up here. I1 doesn't touch it. I2 does, and it goes in the same direction, so it's positive. And I3 doesn't touch it. So I short circuit is just I2, and that's it. So I can take I2, 1.04, and I can label my Norton equivalent circuit with that current. Okay, next thing we got to do is go find R Norton. And we've got three methods we can use. There are no dependent supplies. Because there are no dependent supplies, we can use any of the three methods. What do I want to do for that? I think I want to... I don't know. Let me copy it for starters. Scroll down here. We got to find R Norton. You know, you could use method 1. You could, if you can see everything clearly. Get rid of where the load was, right? Because that's where we're interested in finding R Norton. So let's see if we can make sense of this quickly. And if we can't make sense of it quickly, then we'll use one of the other methods. That might be a little more reliable. In any of the methods, we have to replace, I guess with the exception of method 2, we have to replace the other independent supplies with their ideal resistances. So that was a voltage supply, so it becomes a short. It's popping up right there. Oh, the sun's out. That's breaking my green screen right there. The sun came out. Happy day. Okay, I'm in a basement. Looks like I need to put more cardboard on that window, just so it gets even more basementy down here. Anyhow, okay, so that current supply got replaced by its ideal resistance. It's an open. And then we have to say, well, what's in series and what's in parallel? I could probably figure this out. Maybe. But it's a little ugly. Like, that's not connected to anything. So we could get rid of it. What's in series and what's in parallel? You know, maybe I'd have better luck if I labeled some of my nodes with colors and went through and asked myself all my favorite questions. Let's do that quickly just as an exercise, but honestly, looking at this, I want to revert to one of the other methods because I'm a little more confident I can get the right answer if we use one of the other methods. Okay, so what's in series and what's in parallel? Nothing's in series with the 1 yet. These two are in series, so that does become a 5. Okay, and then that would be in series with this 5, so this would all be 10, and that would be 10 in parallel with 4. 10 in parallel with 4 and series with 1. Oy. So we could... that's a big pen. All right, so we could do method 1, and if we're really sharp, we could say Rn is 3 plus 2 plus 5, because those are all in series, right? For a total of 10. That's going to be in parallel with 4. Get some square brackets in here. And that's going to be all in series with 1. Whatever that ends up being. Let's see what it is. 10 in parallel with 4 plus 1. Okay, so that tells me that R Norton is 3.8. I'm going to round to 6 ohms. Okay. Maybe you're good at that, maybe you're not. I had to stop and think about it. I had to color the things in. I'm not saying I'm the best in the world, but I think I have a little more experience at this than you do. You're getting experience right now. Okay, so my other option would be to use one of the other methods. Okay, and let's grab this. Unfortunately, it's going to have the colors on it, but you know, there's worse things in life. I could just as easily use method 2 or 3. I think I want to use method 3 and just throw a voltage supply in here. Right, I knew I'm going to pick 42 volts because why not? I can pick whatever I want. And then we do some analysis, right? That's I1, this is I2. Ooh, there's only 2 meshes. That's nice. That current supply took out a whole mesh for us. Good stuff. Okay, so let's see. No current supplies. So what is I1? So 2 KVLs. First one, KVL around I1. What does I1 touch? 2, 3, 4, 5. So that's going to be a total of 14 again. What does I1 share with I2? It's going to share the 4. What does I2 share with I1? -4. What does I2 touch? It touches a total of 5. I don't know that I left myself enough room. You know, I made some big boy choices, and now I'm going to live with the consequences. Okay, so no voltage supplies on the first mesh. I'm going down 42 volts on the second mesh. -14, -4, 0, -4, 5, -42. All right, so from that we get I1 is equal to -3.11. That's repeating, but we'll round there. And I2 is -10.88. Also repeating. These are both in amps. So I'll try to squeeze that in there. And we'll try to squeeze a square bracket right down the side. I'm getting a little better with this tablet. Okay, and I'm going to store those for later. Okay, here's V new, right? That 42 volts is V new. And then we go calculate our Thevenin as V new over I new. Okay. Okay, so we know V new, we pick that, that's 42 volts. And I2 and I new, are negations of each other. So we're going to have in the denominator positive 10.88 amps. Okay, it takes a little bit longer, but if you can't see the relationships, this is a great way to find this resistance. Okay, 42 divided by -I2. And we get, who would have thought, we get 3.86 ohms. Just like we did using method 1. Okay, so now I've done it twice. I'm feeling really confident. That's when I'm most likely to screw up, is when I'm feeling really confident. Okay, so 3.86 ohms. So we can take this whole circuit and drop it down to 3.86 ohms in parallel with a 1.04 amp current supply. Okay, but that's not what we're trying to ask. That's not the question we are trying to answer. What is the maximum power RL can dissipate? So I'm going to take that Norton equivalent. I'm going to slide down here to the bottom. If I have any room left, I do. Happy day. Okay, and we'll clean this up because it was all crammed in there. In order to maximize power, we're going to make this load have the same resistance as the Norton equivalent resistance. Okay, now all we got to do is figure out how much power is being dissipated by that load. And look at this, we have a current divider. So what I would like to do first, because I think it's the easiest, is to find the current through that resistance. Okay, so this is nice and easy because it's a current divider and the two branches are equal resistances. So I know that in this case, IRL is going to be equal to 1.04, right? And it's going to be 3.86 over 3.86 plus 3.86. So it's really just going to be half, right? Half of 1.04. My coffee's wearing off. I don't trust myself to... I would have gotten it right. Yeah, I would have gotten it right. I should have just done it. I would have looked better, right? It's okay. If you have a tool, use it, right? If you're not comfortable doing something, then you know, learn how to use your calculator correctly so you don't get it wrong, but use a calculator. Okay, 520 mils for the current through the load. Okay, now I could go find the voltage and all of that stuff, but I think what I would rather do is use one of those forms of power that absolutely ruins the passive sign convention, but it'll work out here. Okay, so the power dissipated by the load is then the current through the load squared times the load. Okay, so that's going to be 520 milliamps squared times 3.86 ohms. Okay, let's see what that is. So square that times 3.86 and we get the right answer. Okay, 1.044 watts. Okay, so hopefully now you understand why we wait to talk about maximum power transfer theorem till we talk about Thevenin's and Norton's, because they are very closely related. All right, sometimes this gets asked in a slightly different way, and I'm going to do an example with that. Maybe the circuit will be a little smaller. I'll do that one with Thevenin just to mix it up. But if you really want, and you're bored, because I know you're bored, go back and rework this with a Thevenin equivalent and see if you get the same answer. It's good times, trust me. It's what I do for fun on weekends. I wish I was joking. Stay tuned and good luck.